Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to do a quick review of deep learning. As you know, deep learning is just a fancy name for neural networks. Neural networks in their simplest form are just a bunch of logistic regression layers chained together. We call the layers in between the input and output hidden layers, and we call this type of neural network a feed-forward neural network. What makes them nonlinear function approximators is that they have a nonlinear activation function in between each layer. These nonlinearities allow us to model highly complex functions, rather than just linear functions. Despite all this apparent complexity, the training algorithm for neural networks hasn't changed fundamentally since we looked at logistic regression. We've made some improvements here and there, but at the core we are still just doing gradient descent. One problem with gradient descent is that it's not as robust with neural networks as it is with logistic regression and linear regression. It's very sensitive to hyperparameters, especially when you have very big networks. There are a lot of different choices you have to make when it comes to neural networks, and it's not clear what works and what doesn't until you try. We can modify the learning rate, the number of hidden layers, the number of hidden units per layer, the activation function, and even the type of gradient descent optimization, like AdaGrad, RMSProp, or Atom. And these different types of optimization algorithms come with their own set of hyperparameters. You will never run out of hyperparameters to try. One setting might yield an accuracy not much better than chance, and another setting might yield a very good accuracy. This lack of robustness often surprises students who are just beginning to learn about deep learning. As with all machine learning models, the input to a neural network is a feature vector X. We like neural networks because they save us from having to do a lot of feature engineering manually. The nonlinear characteristics of neural networks have been shown to learn features automatically and hierarchically between layers. For example, if the input is an image, the first layer might learn some edges at various angles, the next layer might learn groups of edges, the next layer might learn facial features like eyes, noses, lips, and ears, and the final layer will be able to recognize faces. Working with images is important. As a human, it's one of your main sensory inputs. As a robot trying to navigate the real world, images are also one of your main sensory inputs. Images also happen to be what the states are made up of in video games, and so we'll need to know how to work with images in order to train agents that can play Atari games from OpenAI Gym. Luckily, we have special techniques designed just for working with images. The convolutional neural network is a type of neural network that does a set of two-dimensional convolutions before going to the fully connected layers. Fully connected layers are the layers that comprise a feed-forward neural network. We call them fully connected because every output from one layer is connected to every input from the next layer. Convolutional layers are different. At each convolutional layer, we have a filter that is typically much smaller than the input image. In addition, instead of working with feature vectors, which are one-dimensional objects, we work with images, which are two-dimensional objects. They can also be three-dimensional objects if they have color. While you probably want to consult my Convolutional Neural Networks course, or a full semester course on signal processing, if you want to gain better intuition about what convolution is doing, here is a simple way to think about it. The idea is we want to take a small filter and multiply it against the original image from all possible points. Basically, that means we're sliding the filter across the image. Aside from this sliding, it works exactly the same as a fully connected layer, meaning all we do is multiplication and then eventually pass it through a nonlinear activation function. Having a small feature like this means that every part of the original image uses the same shared weight. Shared weights allow us to have a model with a much smaller number of parameters, which means it takes up less space and trains faster. In reinforcement learning, we aren't just interested in images, but sequences too. An episode is made up of a sequence of states, actions, and rewards. The appropriate tool for working with sequences in deep learning is recurrent neural networks. Any type of neural network where a node loops back to a previous node is recurrent, and we call such a connection a recurrent connection. Typically, we don't think in terms of individual recurrent connections, but rather entire recurrent layers. I taught you in my course on recurrent neural networks that we treat these layers like black boxes. It's helpful to think of a recurrent layer as just a box that takes in an input and produces some output. The fact that the output depends on previous inputs as well means it has a memory of what it's seen in the past. This can be particularly useful in the context of reinforcement learning, since it allows us to make decisions on not just what we see now, but what we've seen in the previous frames as well. In most of my previous courses, we focused on multi-class classification, where we had multiple output nodes and performed softmax at the final layer so that each output node could be interpreted as the probability of the input belonging to a class. As you know, in reinforcement learning, we want to do regression on a real-valued scalar to predict the value function. That means instead of having multiple output nodes, we'll have just one output node, and instead of using cross-entropy error, we'll use squared error. Now remember that this review section is only for the purpose of helping you review topics that you already know. It's not meant to teach you anything new. So if there was anything in this section you didn't know already, you are in big trouble. If this is the case, you should not proceed with this course until you study the prerequisites.